Riemann's formula. He was a student of Gauss, and he developed this formula. Remember, Gauss did a curvature of a two-dimensional surface embedded in three-dimensional space, and then Riemann generalized it for any kind of dimensions, and also for intrinsic curvature, not only a two-dimensional surface in three-dimensional space, but a two-dimensional space intrinsically curved, a three-dimensional space intrinsically curved. Okay? Before we had how many curvature terms? We had only one when we had two dimensions, because it was only r and theta, so there's only an r theta term. That's it. Now that we have r theta and phi, we have how many terms? Three pairs: r theta, r phi, theta phi. Okay, before we had only one. Okay. Now what this Riemann tensor component gives you is the AB component, meaning, let's say it's the t theta curvature within the r theta t phi space. All right, so it's not exactly a two-dimensional surface, but it's a two-dimensional curvature. It's kind of like a surface, the tr surface, so to speak, within tr theta phi, and the theta phi surface within tr theta phi. So, all right. For the diagonal components of the Riemann tensor, the AB ones, not ABCD or ABDC or whatever, but where like TR or theta R and so on, all right? If you look at Riemann's formula, all right, it seems very, very complicated. If you've seen the Riemann curvature tensor and so on, you have all these gammas and so on and all these G's, and it's not very intuitive. I've written the formula in a different way than it's usually done. It's much simpler. And I used that also, and I ended up with something really, really nice. Basically, it's built on extending it from Gauss's formula. I didn't actually start out from that. I ended up realizing that that's what I arrived at. Okay. In order to have the curvature of a higher dimensional space, all right, we're going to base it on this original formula of Gauss for a two-dimensional space. We're going to add on an additional term. This term is a product of two gammas, but it has to be summed. There's really gamma times gamma plus gamma times gamma plus gamma times gamma, whatever. Okay, with the appropriate subscripts and so on. It's composed of two pieces. This is the piece which exists even if there was only two dimensions and it was a two-dimensional space or a two-dimensional surface, plus an additional piece which exists because there are other dimensions.
What is the comma r, comma t after the GTR over GR?
Yeah, what is that?
Is that a component?
Oh no, that's a derivative of r. Actually.
Derivative with respect to r.
Yeah, derivative with respect to r.
Okay, if you have a comma r in a subscript, it means derivative with respect to r. The formula that I found was this. It turns out to have a very nice structure. And it's a derivative of the gamma. And these are products of the gammas. So you can see the general structure here. You have the term in there, the gamma prime plus gamma prime term that Gauss had for a two-dimensional space, two-dimensional surface in three-dimensional space, plus the additional term that comes in when you're in a higher dimensional space. Okay?
What are these terms? These are the gamma-gamma terms. These are similar to the gammas, the connection coefficients, the derivative with respect to g over g. And this is a derivative of the gamma. This is a gamma.
Now this already has the form that we expected, which is a gamma prime plus a gamma prime plus a gamma times a gamma. And remember, this gamma times gamma is really a sum of a few. We're summing over all the coordinates d that aren't a, b. All right, and again, this will be a little bit more clearly as we work out the problem. What is the formula for the Riemann curvature? Now, in the cases that we're going to do, because we have no mixed term, what we want to find are these Riemann tensor components. They have 4 indices, the a, b, but the indices will repeat because we have an orthogonal system, because we only have the x, dx, the x0, the x0, the dt, dt, whatever, the r, d theta, d theta, d phi, d phi. The Riemann tensor components will also, basically, the ones that we need will be the ones that have repeating indices, the a, b. All right? As we saw before, what we're going to expect are a sum of derivatives of the connection coefficients and products of the connection coefficients. And we spoke about where that comes from, let's say, in gravity theory, but this is also known in Riemannian geometry, differential geometry, that this is, in fact, the formula for a Riemann curvature based on the connection as a function of the connection. It's simply this function. We saw, heuristically at least, reasons why this makes sense in the context of gravity and so on. But you can just accept it as differential geometry. You know, you can prove that the Riemann tensor components are composed in this way of the connection. We also know that the connections are composed of the metric coefficients. And therefore, if you plug in, it's like each gamma is like a g prime over g. So if you plug in the g prime over g into these gammas, then you'll get this formula, okay, which is in terms of the g's. So this is the formula for the Riemann tensor components in terms of these metric g's. We only have 2 g's to find, okay? So it's not going to be such a difficult formula. You can see kind of intuitively, in a sense, how that would take into account the curvature. It's how each of those metric coefficients change with respect to one or other of the other coordinates, normalized out either by itself or by the g of the other coordinate. And that's exactly what these connections do. And the derivatives of that, or the products of that, are the curvatures. And when you compute the Einstein equation, what you're doing is basically computing those terms. Derivatives of the connections, products of the connections.
So the Riemann tensor is composed of components which are a piece which comes from the same kind of curvature that would exist in just regular Gaussian curvature of a surface. But this is, of course, intrinsic curvature of a space. Plus a piece that comes from the fact that it's really more than just 2 dimensions. For example, in spacetime, you have 4 dimensions. These 2 dimensions, that are represented by the indices a and b, those coordinates, have this curvature just by their own interconnection. And that's where the second derivatives come in. You have a derivative with respect to b, derivative with respect to b, so you have a second derivative here. Here you have derivative with respect to a, derivative with respect to a, second derivative. These terms have only first derivatives, products.
In all this complicated looking formula, you have basically 1, 2, 3 terms, or whatever. You have a derivative, and a product. Remember, we're always going to see those in curvatures, Riemann curvatures. We're going to see a derivative of connection plus a derivative of connection plus a product of connections, where connections are basically g primes over g's. All right, so you can have in that basically first term ga comma b over gb, all that comma b. Okay, that's the ga comma b over gb is a connection, and the derivative of that is a derivative of connection. Similarly, you can have a gb comma a over ga, that's a connection. The derivative of that will be the derivative of connection. The next term you'll have ga comma d over ga, that's a connection, and gb comma d over gb, that's another connection, so that's a product of connections. We're always going to see that gamma prime plus gamma in the curvatures. Okay?
All right? This is exactly the same as Gauss's formula for the 2-dimensional surface. You have the derivatives of the a part of the metric with respect to the other guy b. You're talking about these 2 guys. So you have the GAA derivative with respect to the b coordinate, and here you have the derivative of the GBB with respect to the a coordinate, normalized by this one and the derivative. And that's exactly the same as the 2-dimensional curvature.
The eta times eta, that gives you just a signature if it's plus or minus. All right, that term that we have to add on, this gamma times gamma term, all right, you have this GD, where D is the coordinate over which we're going to sum. All right, we're going to have a product of 2 gammas, GA comma D over GA, and GB comma D over GB, right? And we're going to sum, we're going to have gamma times gamma for D, any D that's not equal to AB. You have this breakdown into two pieces, the derivative of the gammas and the product of the gammas. Okay. When you have derivatives of the gamma, you're going to need two terms. The gamma, one gamma derivative with respect to the other guy, plus the other gamma with respect to the first guy. And then a product of those two, and it's really not a product just of two, it's a sum of products. It's this gamma times that gamma plus this gamma times that gamma.
The
What
TR,
do you do with the D, you sum over the D?
right, you're summing over, if this is, let's say, TR, so all of this is TR, TR, TR. These are the ones that are not TR, like theta phi.
And you sum.
Yeah, and you're summing. So these derivatives are only for coordinates where both the A and the B metric coefficients have derivatives for that coordinate.
Now, if you notice, if D can't be AB, then in a two-dimensional space where there's only two things, then D can't be anything, which is why this term doesn't exist for the Gaussian curvature. Okay. So by adding those two terms on, we get this formula for the Riemann tensor component RAB-AB. Now, if you look at it, there's a few things to pay attention to. One is the symmetry. If you change A to B, the whole thing stays the same. Okay? Also, in the next term, you have GAD over GA comma D over GA times GB comma D over GB. Remember, we're going to sum over D. D is going to be something summed over. It's just A and B. Again, it's exactly the same thing. If you switch A and B, those two terms are the same. So therefore, can you see why if one switches A and B, the formula below will get the same result, okay? Basically, you can see that it doesn't matter if you took A and B or A, it makes no difference. So this is something that appears in this Riemann tensor component. So if you have, let's say, R theta, it doesn't really matter which one, if it's theta, R theta, it doesn't matter if you switch them, because these terms in that computation will be symmetric in that interchange. And I'm not going to worry about plus and minus signs and so on. I told you that at the beginning. Basically, it remains the same thing. Except that A to A, A to B. Pardon me?
So it's kind of like a commutator.
Well, there are commutators in here, you're right.
You can find this formula in various ways by deriving it firsthand. It took me a long time until I finally found it. And then I ended up realizing that people had found the Riemann tensor components for orthogonal coordinates or diagonal metrics. And if you just use these square roots instead of the G's, you end up with my formula. So for example, you can look at Landau-Lifshitz. In Landau-Lifshitz, he has this formula for orthogonal metrics. If you use the square roots and you cancel certain things and so on, you'll find my formula. In my formula, I'm using a non-standard notations like Fierbeins, where you're using just one index. These are the positive square roots of the metric coefficients, which usually have two indices. Right?